Hello, everybody, and welcome to yet another lesson in contemporary math. In this video, I will be going over lesson 8b, doubling time, and half-life. So we could think of this as doubling time and halving time. So we've already talked about exponential growth and how that means you are increasing. So exponential growth leads to repeated doubling, and exponential decay leads to repeated halvings. So if you decay, that means you're decreasing. And a big deal in the decreasing world is decreasing by half. So let's start out with the doubling time. The time required for each doubling in exponential growth is called the, you guessed it, doubling time. For example, the doubling time for our magical penny was 1 day. And for the bacteria in the bottle was 1 minute. So here is a very quick example with everything worked out. Consider an initial population of 10,000 that grows with a doubling time of 10 years. So what happens is in 10 years, or 1 doubling time, the population increases by a factor of 2 to a new population of 20,000. But if you let the doubling time happen twice, in this case 20 years, it would double after the first 10 years and then double again after the second 10 years to 40,000. And you can see that would happen, the population increases by a factor of 2 squared, which is how we get the 4 for 40,000. And something very similar following the pattern, in 30 years, or 3 doubling times, the population increases by a factor of 2 to the third power, meaning we would have a population of 80,000 people. So one thing I want to point out is, for 1 doubling time, the exponent on 2 was 1. For 2 doubling times, the exponent on 2 was 2. For 3 doubling times, the exponent on 3 was 3. So the number of doubling times that you have is the exponent on 2. So let's take a look at what happens with the calculations with doubling time. So calculations with doubling time, after time t, an exponentially growing quantity with doubling time of t sub double, so the capital T will be the doubling time, increases in size by a factor of 2, little t over t, the doubling time. The new value of the growing quantity is related to its initial value at t equals 0 by this equation. So to see how this works in action, let's take a look at this next example. We have compound interest that produces exponential growth. Because an interest-bearing account grows by the same percentage each year. Suppose your bank account has a doubling time of 13 years. By what factor does your balance increase in 50 years? So to figure out the factor, the growth factor, I want to point out where that is in this equation we just looked at. This would be the growth factor. So all we have to do is figure out 2 to the how long are we holding our balance, 50 years, divided by how long does it take for the account to double, 13 years. So we would have 2 to the 50 over 13 power. And in plain numbers, that is about 2 to the 3.8462 power, which you can figure out on a calculator is 14.382. So your money would grow in this account over 50 years, it would grow 14 times over. which is huge. If you can find an account that does that, put all your money into it. To open up this slide, we have an approximate doubling time formula. So you can see we will consider a study of prairie dog community. There are 100 prairie dogs when the study begins, and the researchers determine that the population is increasing at a rate of 10% each month. So here you can see we have a table, and it's in 2 columns. So here's our split right here, in that the population starts at 100, and then after 1 month it is 10% more than that, and after 2 months it's 10% more than the first month, and after 3 months it's 10% more than the second month, so on and so on and so on. So in all of these equations you can see that each equation has a 100 here. And this 100, of course, is the initial population. When the study begins, there were 100 prairie dogs. But this 1.1, where does this 1.1 come from? When we are dealing with exponential functions, we know that there is a 1 plus the rate to some power t. And t can represent months or years or whatever. But r is the rate at which the population or whatever it is increasing or decreasing. So in this case, because it's increasing, we know it's going to be a plus, and 10% is 0.10. So this is our rate, and we know it has to be positive. So if we add 0.10 to 1, that is where the 1.1 comes from. The next question, and we don't even have to do any math for this since we have a table here for us. Approximately when does the population double? Well, if the population starts at 100 and we wanted to double, that would mean we are looking for when the population becomes 200. And that is somewhere between month 7 and month 8. We don't have an exact month for that, so we just have to say between 7 and 8 months. Then we are looking for the population to double again. So you can see here we have the time it takes to double from 100 to 200 is between 7 and 8 months. If you wanted it to double again, we would have to go from 100 to 200, and when you double 200, you get 400. So if you look right down here at months 14 and 15, there is the second doubling. It is somewhere between 14 and 15 months. Now, as I scroll down here, we can talk about the approximate doubling time formula, aka the rule of 70. So here we have, for a quantity growing exponentially at a rate of p% per time period, the doubling time is approximately 70 divided by p. Again, p is some percentage rate. This approximation works best for small growth rates and breaks down for growth rates over about 15%. So the question is, does this formula agree with our findings above? So if we take this particular expression here, and we say 70 divided by, it was 10% growth rate, so our doubling time is roughly 7 months. Does that agree with what we saw up there? Well, yeah, between month 7 and 8, it had doubled. And between month 14 and 15, it had doubled. So yeah, that works with what we found. And one more example of this, we can use this to figure out world population. We can deal with huge numbers, like the world population reached 7 billion people in 2012 and was growing at a rate of 1.1% per year. What is the approximate doubling time at this growth rate? So all we have to do is we have to take 70 and divide it by our growth rate. And this time we do not move the decimal anywhere. I took the percent from the previous example up there and put it in this equation. We got 7 months, and that was about right. So we just take the percent. We don't change anything. And that ends up being about 64, in this case, years to double the world population. From here, we move on to exponential decay and exponential half-life. Exponential decay occurs whenever a quantity decreases by the same percentage. Important because this will still be an exponential function in every fixed time period. In that case, the value of the quantity repeatedly decreases to half its value, with each halving occurring in a time called the half-life. Now, if any of you do play the video games out there, Half-Life is for real represented by this little lambda, and I don't remember how this fits into the title of the video game or how it does with the video game. I can just tell you that for sure this is the symbol used in science to represent a half-life. So very first thing, just a few explanations. Radioactive plutonium-239, Pu-239, has a half-life of about 24,000 years. Suppose that 100 pounds of plutonium-239 is deposited at a nuclear waste site. The plutonium gradually decays into other substances as follows. In 24,000 years, or one half-life, the amount of plutonium-239 declines to 1/2 its original value, or to 50 pounds. We will continue this example on the next slide. Before I get there, the same thing happens with the number of half-lives being the exponent on the value 1/2. In 48,000 years, or 2 half-lives, the amount of plutonium-239 decreases to 1/2 squared its original value, or if you square 1/2, you get 1/4. And 1/4 of 100 pounds is 25 pounds. And then we have this statement here that just furthers our pattern. We can keep taking half of the value before it. So we have calculations with a half-life. After time t, an exponentially decaying quantity with a half-life of t sub half decreases in size by a factor of 1/2 to the little t over big T. The new value of the decaying quantity is related to its initial value by this equation. So we would have the initial value times some sort of half raised to some power, and that would give you the new value. So here we have one example, and I'm going to scroll up just a little bit, and this will be, it looks like, the last example for this video. The half-life of a drug in the bloodstream is 4 hours. What fraction of the original drug dose, remains in the bloodstream after 24 hours? How about 48 hours? So what we can do then is that we can know that these are little t values and that the half-life is the big T value. So what we can say then is the half-life is 1/2, and we can take 24 and divide it by 4. And this will give us the fraction of the original dose remaining. So this would be 1/2 to the 6th power, which would be 1/64. So you would have 1/64th of the original drug in your bloodstream. If you beef that up to 48 hours, that means you would have 1/2 raised to the 12th power. 48 divided by 4 is 12, which is 1/4096. This is the fraction of the original drug dose in your bloodstream after 48 hours. This is virtually nothing. There's virtually nothing left. So to think of these in terms of percentages, when you take a dose of this drug with a half-life of 4 hours, after 24 hours, about 1.5% of the original drug remains in your bloodstream. And after 48 hours, only 0.0244% of the drug remains in your bloodstream. And this is like a very real application of half-life. If you've ever read on any medication bottle, don't take more than this many doses in 24 hours. Make sure you're taking these doses with 4 hours in between them, or 6 hours in between them, or the 12-hour allergy medicine. They put those time limits on there so that enough of the drug has been out of your system that if you take another dose, there won't be too much in your system. And this concludes the lesson for section 8B, diving deeper into exponential functions and doubling times and half-lives and how they work. I hope this video was understandable for you. Good luck.